playa someplace. And in Las Vegas, some of us would be bailing out of our flooded homes. So we actually have a very timely and relevant subject today on flash flooding and how flash flooding risks are increasing with climate change. So I'm very happy to welcome our guest speaker today, Ji Lee. Ji's research interests are focused in remote sensing and hydrology, extreme weather events, which we have all experienced recently with hurricanes and flash floods in Las Vegas and flooding up in Reno and in northern Nevada, and how climate change is going to impact those studies. I know that's becoming more of a problem on some of my DOE federal work too. Dr. Lee is currently on his way, literally, to Stanford as an incoming postdoc research associate. So Guo met Ji at a conference, at AGU conference, and they've become kind of professional colleagues. And so on his way from the University of Oklahoma, where he just finished his PhD in 2022, he stopped in Las Vegas to do this lecture for us today. Dr. Lee has actually been named the recipient of the Stanford Dior School of Sustainability Dean's Postdoctoral Fellowship. So this is a pretty big deal, and we really appreciate you spending your day with us here. He's published over 20 journal articles on this subject and has been an invited book chapter author. His research has been featured in the New York Times, Washington Post, on AccuWeather, and on CNN. So his research is actually very well received. And again, very timely for this time of year in Las Vegas and in Nevada as a whole. So thank you. Please welcome Dr. Lee.
Yeah, thank you. Thanks for the introduction and the invitation to give this talk. So yeah, just to jump to the topic I'm going to cover today about flash flooding in different places around the country. And I know many of you have experienced the flash flooding here last few weeks. So hopefully this talk can generate some interest from both parties. Then today my talk covers 4 parts, and in the first part, probably I'm going to spend 50% of the time talking about how we define a flash flood, because sometimes the definition of a flash flood is vague. I will talk about it later. Then I will introduce a novel method I proposed called the flashness intensity duration frequency curve. Then the second part will focus some more on the climate change impact on the flash flooding. Then briefly, I will just showcase some of the impact of flash flooding on the tribal people in Oklahoma. Then followed by the closing remarks. Obviously, some of you have you have experienced this flash flooding in the I-15, so it caused a lot of traffic. As you can see on the left, that's the picture taken from probably a camera showing the flash flooding causing and the flood rivers. And on the right side, you can see those traffics caused by the flooding. And on the right part of the figure, you can see those are the operational flash flood forecast system. And as it indicates, it has over 200-year return period for this event along these borders from California and Nevada. Even more recently, we had several storms on the West Coast and on the East Coast. On the West Coast, we had the tropical storm Hilary, causing a lot of flash flooding in the deserts. And on the East Coast, we had Hurricane Idalia, probably still going on several days ago. Then let's dive a little bit more about the flash flooding. How can we define the flash flooding? The definition, as I said before, the definition of flash flood event is vague. As you can just Google it from online, you can see the National Weather Service defined it a flash flood event as the flooding begins within 6 hours and oftentimes within 3 hours of the heavy rainfall. But as for me, as a modeler, I don't know how to put this sentence into my models because you have to define what is a rainfall event, what is a rising peak time, and what is a flood, what is a flood peak, so on and so forth. So that is a common problem and issue for us. As a result, if you look at, some of you may have used this National Weather Service storm reports. It reports the flash flood events over the country. And as you can see, the big chunk of the West Coast, especially Pacific West Coast, they have 0 flash floods. That's not true, right? Because we don't think we got the definition of flash flood right. So people there, they don't report flash flood events at all. So what does National Weather Service forecaster do? They're just looking at the so-called flash flood guidance and to see if the threshold is surpassing that flash flood guidance threshold, then they may issue the flash flood warning. And they hand draw those warning boundaries as you may receive from your cell phones, those warnings. Let's take a step back. How do we define a rainfall? Some of you deal with extreme rainfall. You might heard this concept called intensity, duration, frequency curve. What it does is that if you look at a rainfall event from 3-dimensional concept, you plot the storm duration on the x-axis and the intensity on the y-axis, then you can get different frequencies of the rainfall event. Then those dots, the black dots, are those real rainfall events, but you can, based on this frequency curve, you can basically select the event that is of your interest. Let's say if you want to study a 100-year, 10-hour rainfall event, you can just pick this line. Those lines are empirical lines defined from, derived from the rain gauges. So you can pick that line and just look back in history, what kind of rainfall event surpassed that line, then you get a 100-year and 10-hour rainfall event. So why can't we just borrow the similar idea and design the flashness IDF curve so that we can define a flash flood event based on the similar concept? That's what we propose here. So before doing that, if you do a rainfall IDF, you know the rainfall intensity as a quantity. But for how to quantify a flash flood, so what we propose here is a flashness index. There are many studies using different quantities of flashness index. But here we just wanted to use a simple one that reflects the nature of a flash flood event. That's basically how quickly and how high the stream flow rises in a flash flood event. And on the right-hand side, you can see it's a typical hydrograph. You've got the rainfall time series on the top, and you got the hydrograph, the stream flow response on the bottom. So this, you can see the rise of the stream flow is pretty quick, and you can define the flashness as the derivative of the stream flow and with regards to time. Then you divide it by the drainage area, because as you may imagine that large watersheds typically don't have really serious flash flood event, because the catchment draining area is getting bigger, then the stream flow response gets slower, and so on and so forth. Then after doing this, quantifying the flashness index, we can fit into an extreme value distribution. Those criteria or steps are basically similar to how do you define a rainfall IDF curve. So you fit a maximum slope over a moving time window. Here, I just propose 1 hour up to 6 hour event, but you can extend that to 12, 24 hours, for instance. And you extract the annual maximum and fit into an extreme value distribution. Here, I just tried several types of extreme value distributions, like the log Pearson type 3 distribution and some derivatives. Then you can find the optimal fit based on some criteria you choose, either AIC or BIC. Then finally, you can derive the flashness values at different frequencies of your interest, let's say 2 years up to 100 years. Then this animation just shows how we scan through different this hydrograph and get to the flashness FIDF values at different time window. Here this shows a 3-hour time window. If you scan it through, it will get different slopes at different time. Then you accumulate that time series of the FIDF, fit into extreme value distribution, and then derive the frequency analysis. So if we compare the rainfall IDF with flashness IDF, you can see they are pretty much the same, because what you found on the y-axis, there's the rainfall intensity, flashness. As you go extend the storm duration, you get less severe, the less stream flow rises, and the intensity gets smaller. So you can basically repeat that process for all the stream gauges in the continental United States. Then you can find this plot on the left is the 1 hour flashness values at different frequencies from 2 year up to 100 year. Then from this plot, you can definitely identify some hotspots, like numbered in the plot. The number 1, the West Coast, and number 2 is the Missouri Valley. Number 3 is the avalanches. Number 4 is the flash flood alley. It's basically across Texas, Austin, San Antonio, those corridors. And number 5, the Southwest. So you got the dry desert, and the flash flood occurs rapidly, especially following those monsoon rainfall. And here's an example for the 2021 Tennessee flash flooding. Based on our concept, there's 1 hour to 6 hours storm duration, and those dots are USGS stream gauges. As you can see, the frequency now marked in the next to the stream gauges. So they're basically from 2 year up to 10 year or even 100 year flash flood event. And I want to point out is that if you look at the top left gauge, for 1 hour and 2 hour event, they're barely considered as a flash flood event. But if you increase the duration up to 3 hours, 4 hours, and 6 hours, they immediately jump to 100-year event. So that's why we think the duration of the event is important, as if you disregard that, like you only use 1 hour, it will just barely issue any warnings for this region. Then the next question is, if we can do that at gauge locations, can we just do it at a distributed manner for the whole country in the United States? Then we definitely can think of using a hydrologic model to fill those ungauged regions, right? Then that's what we propose here is a distributed FIDF product. And we adopted 2 approaches. One is using the hydrologic model. Here we use a CRISP model. It's our in-house hydrologic model. And on the right, we propose a machine learning base to emulate the quantities of FIDF and to derive the stream reaches based FIDF product. Just wanted to briefly talk a little bit about the hydrologic model we're using here. It's called CRISP, Coupled Routing and Access Storage. It's a joint product by University of Oklahoma and NASA. And over the 10 years, it has spanned and evolved a lot. So it just evolved to version 3.0 and has been coupled, integrated into other models, environmental models. Like it has been coupled with landslide model to produce landslide warnings, which has been adopted by NASA. And it also has coupled into land surface model. And what we use here is called a EF5 ensemble framework for flash flood forecast. This is an operational flash flood forecast model adopted by NOAA, National Severe Storm Laboratory. And from some of the early studies, it has found that it outperforms traditional distributed the flash flood guidance by those weather forecasters. Then annually, they're doing like training sessions for the weather forecasters to issue flash warning based on this product. So just briefly show you the results. We can, once we get the hydrologic model set up, or we can have the machine learning model to predict the flashness. It's basically a static feature because once the gauge locations are the same based on the geography of the gauge locations and also some climatological features. So we can basically derive a distributed FIDF product. So on the left is from the hydrological simulation, and on the right is a machine learning based FIDF. So because there are some gaps for the hydraulic simulation because we're using the radar QPE to run the model. Some of the mountainous regions, especially over the Rockies, they don't have radar coverage. So that's one of the limitation of this work. But for the machine learning derived FIDF, you can see it's basically spanned over the country. And you can also spot out those flash flood hotspot regions in this country. And by basically applying that similar idea, we do a real case example for 2009 Louisville flash flooding. We just validated our distributed FIDF with stream gauge derived FIDF. There just has some similarities and differences. As you can see from the less than 2 year event, the model basically over predicts the flash flood event, but the stream gauge is not saying any flash floods. That's understandable because some of the stream gauges are controlled by upstream dams and hydraulic infrastructures. So our models currently don't have that capability to simulate the human impacts on the stream flow. So that's one of the caveats. But for the 100-year event, you can see the model and the gauges agree each other pretty well in that sense. So that is the first part. I just briefly talk about the recent research I've been doing at University of Oklahoma. But if you want to know more, happy to share more of the manuscripts with you, so we can find a way to work on some of the future endeavors. And the second part I'm going to talk about is the climate change impact on the flash flooding. As you can see, there are several challenges for flash flood projections. If you use a model, you can see those model resolutions are over 100 kilometers, and they are not suitable for flash flood projection because you're thinking of a flash flood scale, which is at kilometer and sub-hourly scale. So those CM5 global climate model simulations are not useful in this sense. So we desire a high-resolution climate projection data set, and we have to acknowledge there are many uncertainties in those climate projections. There are internal uncertainties and different dynamic evolution and thermodynamic impacts basically will bear in the model simulation. Then there's the lack of continuous stream flow simulation in the modern climate models. As you can see, they only consider a coupled atmosphere and land surface, not including the stream flow, because it's basically very time consuming to simulate those stream flow if you do the routing process. Then it has resulted in a few studies, basically quantify the changes in flash floods. So what we propose here is a dynamically downscaled climate model by some folks at NCAR. So they use the retrospective simulation forced by 6 hourly error interim reanalysis data as a control run from 2000 to 2013, and they adapted a pseudo global warming scheme. It's basically just to perturb the boundary conditions. You use the future climate signals and perturbed and forced into weather forecast model, so that you can just mimic the future changes in the thermodynamics of the atmosphere. Let's say if you have the moisture increase by 7%, so you just enforce that 7% change into the model, but it still simulates the current. So if you have a rainfall event happen during 2013, it still can be represented in the future simulation, but at a higher warming rate. And using that, we drive our flash flood forecast model. This is just the EF5 I mentioned earlier. And for the simulation period, pretty similar to the weather forecast model from 2020 to 2001, 2013, with first year as a warming up. So the model, we use the Snow 17 plus the CRIS model. The resolution is at 1 kilometer and hourly. Yeah, I forgot to mention the weather forecast downscale weather forecast model is at the 4 kilometer scale. So we're able to drive that into our kilometer scale at basically a flash flood scale study. Then the inputs are precipitation temperature from different runs, the control run and the pseudo global warming run. And the outputs are obviously the stream flow and soil moisture. Then we still apply the similar concept using the flashness index. Then on the left-hand side, you can see this is basically a hydrograph and from the current climate, and on the right is the future simulated hydrograph. So you can see that it has higher peaks and faster flood rising time, which will result in the larger flashness index. Then we also quantify the spatial scales of rainfall and floods. On the rainfall spatial scale, you can see this, if you just plot the rainfall field, you can easily do a, let's say just using a filter to kind of calculate the distance between the centroid and the edges, the vertices. Then you can search the rainfall areas for those extreme rains, find out the areas of your interest, let's say 2-year extreme rainfall. You can basically find out the spatial scale of the spatial rainfall. But for flood spatial scale, it just applies more steps. You have to first compute the flood threshold based on the simulation, and then create a binary co-occurrence matrix. Then you use a machine learning method. It's basically unsupervised machine learning method to cluster different flooded points with this dbScan model. Then you can calculate the central point to the edge point as your flood spatial scale. Then by looking at the results, so here just shows the rainfall changes, percent changes, event rainfall and percent changes at mean and extreme conditions. So you can basically see a lot of regions are undergoing winter future rainfall. So especially over the Great Plains and east part of the country, you can see a lot of increase or significant increase. And there's a median of 24% of changes in extreme rainfall in the future. That's basically from the model simulation, the WRF model simulation, not from the model itself only considers the thermodynamic changes, not considering the dynamic changes. So if you have let's say, storm track changes or large scale atmospheric circulation changes in the future, those are not considered into these results. So it only speaks for the thermodynamic changes. And for the spatial scale of the rainfall, it's all increasing. And I just ranked here from the west to the east in the Pacific Southwest, Pacific Northwest up to the Atlantic region. You can see there's increasing trend from the west to the east. And if you plot out those rainfall maps, you can see why you got doubled or tripled changes in spatial scale. Is because those isolated rainfall storms in the future and in the past are going to be collected into one big single system in the future. That's what we observed here. As you can see, for instance, the top left one is all collected, and so you got the boost in future rainfall scales. And there's a distinct feature we observed is that if you only look at rainfall changes, the west changes less than the east. As you remember from the previous plot, there's an increase in trend changes from the west to the east. But for the flood, it's opposite. So you got a greater changes in the west, but lesser changes in the east. What's happening over there? So basically, it tells a story that you can not those floods are not only driven by atmospheric inputs, but also the land surface changes. And unfortunately, those land surface, such as soil moistures or groundwater levels, are projected to be wetter in some of the Pacific regions. I know this is contradictory to some of the studies found in the Central Valley. So they say a decrease in trend in groundwater, but from this our model inputs, it's the opposite. It projects a wetter future land surface. So that's basically tells you the uncertainty of different climate projection data, right? If you only use the global climate data, it might just predict a drier future in those regions. But if you add only the thermodynamic changes, it will increase the precipitation and wetten the land surface. So, but the story here, the point I want to highlight is really if you cannot isolate the flood response by looking at the rainfall alone. You have to assimilate those into the land surface models. Otherwise, it may give you falsification of those conditions. And by looking at the flashness, this you can see this plot, it's changes in flashness values in the future. Basically, it projects to have flasher flood in the future by on average 8% flasher at the end of this century, assuming a high emission scenario. And the Southwest has the greatest change, a great increase in flashness among those historical flash flood hotspots. And the central US is going to emerge as a new flash flood hotspot in the future. Then the third part, I just briefly talk about the impact on the tribal people, because I come from an indigenous community in China. And when I got here, I just had those connections with different tribal people in Oklahoma. As you may know, Oklahoma houses 38 federally recognized Indian tribes and named here. So there are some of them are civilized. Let's say the Sharik or Cheyenne, those tribes, they have their own resources. They develop their own models, tools to assess the climate impact on their people. But there are some disadvantaged tribes, like the one we're working with, Oto-Missouri tribe. They're basically a small tribe, and they don't have the resource and the tools to develop their own models or any climate mitigation plans. So that's what we are focusing on. We're trying to bring the equality of this feature, so-called climate justice issues in this country. And as you can see from the vulnerability plot on the right bottom, Native people in Oklahoma has the highest vulnerability among different ethnic groups, followed by some Hispanic and African people. Then the framework we follow here is very similar to what has been proposed in the IPCC. So the risk is considered as three parts: the production of hazard, exposure, and vulnerability. So the vulnerability, we use the SVI indicator, and for the hazard, we had this flash flood model I just mentioned previously for the current climate and the pseudo global warming scenario. And the exposure is just basically look at the number of people being affected by the flooding or extreme rainfall. Then we can come with some of the different risks we plotted here are the extreme rainfall impacts, floods, and flash floods. So you can see there's a greater increase in the climate risks of 80% of increase in extreme rainfall on the tribal people, 137% increase of floods on tribal people, and 10% increase in flash floods on tribal people. And we can also expand this research in the different tribal people in the United States, and by looking at how they are being affected by the climate extremes. Then we found that we just ranked different tribal nations in Oklahoma, found out our Iowa nation tops in the race in the future. Then you may just wonder how is this compared to other ethnic groups in Oklahoma. So that's what we did further by looking at the increase in risks for different ethnic groups. You can see the impacts for the tribal people really, is about doubled the increase than other all ethnic groups in Oklahoma. That's a terrifying message. Then I think that's basically what I wanted to talk for today. And to close, I just have some takeaways and opportunities. Just look forward to cooperating or just having these conversations with you. The main takeaway messages are we just proposed this new method to identify flash flood events based on our in situ observations and models. So basically you can use this method. It's, by the way, it's model agnostic. You can apply it to different models so that you can derive the FID product for your interest. And those can be very useful for emergency responders and weather forecasters. And second, US floods are becoming flasher. As I mentioned, you can see the changes in flash floods in the future. That's about 8% average flasher in the future. And extreme floods are more frequent, widespread, but yet less seasonal. That's the changes in the flood regimes. I didn't show it here, but in our previous studies, we just identified that the seasonality of those extreme rainfall and the floods are changing. It's not going to be like you say in summer you got this monsoon rainfall or monsoon flooding, and in the future it might changes. It may not going to be happening in September. It might be happening in October or earlier, even earlier, depending on different conditions like the snow melt or changes in the dynamics of the monsoon system in the future. And fourth, since the flood generating mechanisms are changing, we need to design our flood measures in evolving manner to cope with those changes. Let's say if you have the snow melt in the future, because of warmer climate, you got more snow melt and drier surface or wetter surface, that you can impact your flood generating mechanisms. But in our in our engineering field, we based on the principles, engineering codes designed 50 or 100 years ago. It's not going to happen in the same way in the future. So we really need to incorporate those climate projection data in order to update our engineering codes. And then finally, the underserved communities are facing greater challenges, and they typically don't have those resources to cope with those challenges. They don't have the resources to design model, to devise any tools or any methods for climate mitigation. But what they have is their lived experience of hundreds or even thousands of years of experience. They know how to cope with, how to deal with nature. They can inform us in the same way that how we can co-live with nature in harmony. And there are some opportunities. So first, I just list some of them here to compare different flash flood forecast products to inform decision making. As you know, we have different types of flash flood forecast models or tools. There are some flash flood guidance and our FIDF product. So we wanted to find a way or an optimal way to inform those weather forecasters, so we can get those flash flood warnings in advance. And second, to compile decentralized flash flood database to advance our understanding. And so right now, those like storm reports are coordinated by the National Weather Service or federal agencies, and there are sometimes disagreements or some disputes about different definition of flash floods or floods. But in our newly designed FIDF, we probably can compile a uniform and for user-friendly flash flood database, and based on which we could diagnose the mechanisms behind those flash flood events, like the atmospheric forcing or the land surface impacts or the environmental change, stuff like that. And fourth, we can understand flash flood regime shift under changing climate. I think in this part is being, I think few studies have mentioned this because of the scale mismatch for flash flood and global climate models. But I believe as we have more computational resources and those global climate models are being downscaled, either statistically or dynamically downscaled, we have more opportunities to couple with couple the model at the flash flood scales, so we can understand how the flash flood regime change in the future. Then finally, how is the flash flood impact on the disadvantaged communities over the globe? And I think there's still a lot of things need to be done for different climate mitigation plans and climate adaptations. And it's in fact one of the major issues undergoing for the national United Nations topics recently. Yeah, I think I'll conclude with these opportunities, emerging opportunities, and feel free to raise your questions and have conversations. Thank you.
Thanks, Dr. Lee. We really appreciate your presentation. We're going to do some questions. I'd like to rotate between Las Vegas and Reno, and then our remote participants too. So anyone in Las Vegas have a question to start with? Guo, of course. There you go.
No, so great presentation. So I know that's why I invite you here. So, okay. I think my question is regarding your definition of flash flooding. So you define a flashness, but that flashness can be think of as the slope of the hydrograph, and then you actually remove the piece of information of the magnitude of those flood flows. So do you think that will cause like an overestimate of the number of flash flood events? Because it's probably some events, it's really flash, but it's not that large. So yeah, that's do you think that will cause those like an overestimation?
Yeah, I think that's a good question. And yeah, of course, you can, whenever you design a new method, there's always limitations and drawbacks, right? And even if you look at the rainfall IDF curve, they still cannot say you guarantee to get those rainfall events comprehensively. And in our methods, we only look at the slope. So that's magnitude could be added as another filter or threshold. Let's say if you wanted to have really a big flash flood event, you look at both ways, both the slope and the magnitude. Let's say the stream flow has to be larger than 2-year flood. So it considered as a flash flood event. So there are a lot of works need to be done. And of course, you can incorporate or coupled with other methods. Yeah, that's my.
Well, after Las Vegas has experienced 2 pretty significant rainfall events in the last month between the hurricane and the monsoonal system that went through late last week, I don't think we are encouraged to hear that flashiness is going to get worse. Reno, does anyone have a question up there for us? I see a hand up.
Let's go ahead, and if you can't hear Connie, I'll repeat the question.
I wondered how well your model method is performing when you run it backwards.
Okay, so I didn't show it here, but we did some validation work regarding just basically extract the information at the gauge locations, looking at the flashiness, and we did say some of the. I don't want to just brag on my product, but it performs very well. But I don't have a number here in my mind to tell you what's the NSE values are or the RMSE values are, but they have been evaluated.
Connie, that sounds like something you might want to follow up with if you're interested. Did we address your concern?
Yeah, thank you.
Thank you. All right, anyone remotely connected? I apologize, we cannot see anyone. So please speak up if you have a question. Anyone? Okay. All right, anyone else in Las Vegas? I see Ted Harwell.
Should I come up there or?
Here.
Thank you very much for this presentation, and I wanted to thank you especially for including the indigenous perspective and impacts as someone who has worked with those communities throughout my career at DRI in the area of anthropology. I really appreciate that. This is not my area of science, so forgive me, but it's tangential to, I think, both the question that was asked in Reno and something you mentioned at the end. I've been an avid watcher of the National Hurricane Center for decades. I love watching, when those tropical depressions form, turn into tropical storms. Seems like we've gotten the tracks pretty well, but something I've noticed that is purely anecdotal and subject to my personal bias of recall is that it seems like over the last 1 to 2 decades, we've done a pretty good job of under-predicting the intensity of the storms in general, especially more than a couple days out. Usually within 24 hours, we've got it figured out. But in terms of, and Idalia was a perfect example where even 2.5 days out, they were still predicting a Category 1 landfall, and that was nearly Category 4. These models any models that incorporate looks at climate change and kind of the additional uncertainty, do they tend to incorporate an additional weighting towards the more recent events in time and the data collected from those events in making their predictions, which again, is probably asking the same thing in a little different way. But.
Yeah, great question. And yeah, I just want to echo your observations. Of course, recently, there have been challenges in storm prediction. I don't know if it's their model or something, because what I found is that I also do did some works in land atmosphere interactions. What I found is nowadays the land conditions are getting more complex. Like you have a flooding followed by droughts, and those conditions, land conditions, will eventually feed back to the atmosphere, and those models typically they're not coupled in a way that more physical way that can resolve those feedbacks. So I think that is an ongoing challenge and will be challenging in a few years or more for the atmospheric communities. I cannot speak for them because I personally didn't do those modeling work. I only do the hydraulic simulation. So back to your question, I think firstly, your observations are true, and for the future, our models, whether they are incorporating the recent events, I would say for the hurricane forecast, like several days ahead, they absolutely are simulating the radar information, the satellite information, the ground gauge information. They do that, but those data in the extreme events are typically very noisy. I did some evaluation of the satellite or radar precipitation, and those data, for instance, in a tornado environment, those debris flows or not debris flow, the debris brought up by the high winds, sustainable winds going upward will just contaminate your radar signal, and those data in those extreme events are typically very noisy. And once you assimilate that information into your model, well, you cannot get to a right answer for that. But our model has some adjustments that are not purely based on the data. They have some weighting or the Bayesian information, like you're using the prior information, not purely on the data it used. So I think there's a lot of things to do for this is another word. Data simulation is a big part. I personally don't want to touch that part because it involves a lot of physics and statistics. So that is indeed a challenge. And what else I can think of? So your question, like whether they are assimilating real data into their models, that's yes. And it depends on the data quality and how recent because they have data transmission delays and how quickly they can update the model and to the system, and whether we can bring those models resolution down to kilometer scale. But right now it's about for the hurricane simulation or forecast about the tens of kilometer scale. But eventually, if you want to force some or to make those information usable for weather forecasters, I think you need to bring that resolution down to kilometer scales so that could be very usable.
So I know in surface water, we always joke about what the roughness coefficient of tires are in channels, but I had not considered that the radar folks had to deal with random paddles and trained in tornadoes and hurricane winds. So, Reno, we have another question up there.
Hey, Julie. Not a question, but a comment. Hi, Dr. Lee. I'm Vic Etemizian. I'm the Vice President for Research at DRI. I wanted to thank you very much for that presentation. My background is not in hydrology or hydrological sciences, so I can't really say anything very smart about specifically your approach and the modeling approach. But what I can say is that in a lot of the work that we do, we're always looking at trying to understand what the impacts of climate change are on various communities, and then also trying to understand how we could translate that climate risk into actionable information for whether it's the local planning authorities or the flood control districts. And I think that the work that you're doing is really very nice in that regard, because it does provide exactly that, a planning tool, an opportunity for people to make the case that their jurisdiction needs additional federal funding, for example, or something along those lines. So I very much appreciate that.
Thank you for a comment. Obviously, those years have been working closely with tribal people and realize they have those disadvantaged positions in the country, and they are passionate. They're very concerned about climate change. That's the passion that drives our research as well, because we definitely want a two-way communication. On one hand, we have those tools. On the other hand, we need their knowledge or indigenous knowledge to inform our climate mitigation plans. I think that's a big part, and will be in the future a lot of research going on in that regard. Thank you.
All right, any last questions from anyone online? All right, well, Dr. Lee, we want to thank you for your presentation. We hope that you continue to think about DRI and hopefully continue to work with some of our researchers here on lots of these subjects. And safe travels to Stanford. Congratulations.
Thank
All right,
you.
thank you.
Good job.
I have no idea what my thoughts was.
Oh, yeah, I think Grant will take care of now.
Yeah, very good, very. I actually, a lot of my work is actually in Fort Lawrence region with Knob Foundation. I Jack is sitting on. Groundwater problems, there's lots of federal case on. Basically providing infrastructure for groundwater, but same thing with flooding and everything else.
Okay, so.
You can imagine people get sick by the water. They have ceremonies to drink the water.
Yeah, so it's just been like great.
Every time you drink it.
You know, I think we're in the US, everybody has.
No, we had that presentation.
Like Jackson, and then we have areas, communities, huge communities, like Navajo Nation, Oklahoma tribes, that